So, do we need general relativity to solve the twin paradox? There are people who say yes, since special relativity can't deal with acceleration, and there are people who say absolutely not. Special relativity can deal with acceleration just fine, or that you can use some trick with triplets to avoid acceleration entirely. Which is a very popular explanation among physicists here on YouTube. So who is correct and who is wrong? And I must admit that I was also confused by this a while ago, until I finally understood why are people divided in the first place. And only when I understood this reason I finally felt that it makes all sense. So what is going on then? Whenever you encounter a conflict like this, it's always useful to go back to the first principles. In special relativity this is very easy because it's made of just two. The principle of relativity, which states that the physics is the same in all inertial frames of reference, and the light postulate that states that the speed of light is independent of the motion of the source. And this is all special relativity is about. It's a theory about inertial frames and how to do measurements in those frames. So, in a nutshell, in special relativity, every observer gets a ruler and a clock that are completely identical. The postulates tell you that all these observers measure that light covers exactly this number of meters in 1 second, using their own ruler and a clock. From this blueprint of how to do measurements in inertial frames, you get all the special relativity stuff, and eventually twin paradox. Okay, now what about acceleration? And there is no problem whatsoever for inertial observer to describe accelerated motion. You just use your ruler and a clock and measure the velocity of an accelerated object in a small time frame and see how the velocity evolves, which is a derivative of 3 velocity with respect to coordinate time. And as the name suggests, this is called 3 acceleration. And although different observers measure different 3 acceleration, it can never vanish once it's there. And therefore, if one observer measures it to be non-zero, then all other inertial observers measure it to be non-zero. You can also define 4 acceleration, which is a derivative of a 4 velocity with respect to proper time. You can think of it as an acceleration you would measure if you were initially in the object's rest frame. This is basically acceleration you would measure with accelerometer. If the spacetime is flat, then non-zero 4 acceleration always implies non-zero 3 acceleration, and vice versa. And when 4 acceleration is 0, then 3 acceleration is also 0. And therefore for inertial observers it's not problem whatsoever to calculate the elapsed time of traveling twin, because inertial observer knows how to measure things. And it's also important for you to know how to protect your network using NordVPN. Today's internet is quite a dangerous place. There is plenty of ads and links and malicious files that you can download, and you shouldn't feel completely safe on the internet without good protection. Even connecting to a public Wi-Fi can be quite dangerous because you don't know if it's not fake and someone just wants to steal your data. For all this, NordVPN has you covered. By single click, you connect to their protected proxy servers that are all around the world. Their threat protection will block ads, protect you from malware and malicious downloads. With NordVPN you can be virtually anywhere in the world, and from my personal experience when traveling, many websites register your position and change their language based on that position, which I find very annoying. But with NordVPN you can always stay at home in online space, or pick any other country you wish. And the good thing is that you get 4 months extra of NordVPN on a 2-year plan, plus up to 20 GB of daily eSIM data using my link nordvpn.com/physics, which you can find in the video description. And it's risk-free with Nord's 30-day money-back guarantee. So, thanks NordVPN for sponsoring this video. So I said that inertial observers have no problem calculating the elapsed time for accelerated observers. So every inertial observer can write down a space-time diagram where he is at rest and everything else is moving, like his twin. And from this spacetime diagram you can calculate easily proper times of each observer, and there is no paradox whatsoever. But yes, if you want to do it properly, so that you also include the acceleration part, you have to use calculus. So many people just neglect this acceleration part and write the diagram like this, which is completely okay because this acceleration part can be arbitrarily fast and should not influence the final result much. The problem is that you can only write such diagrams for inertial observers. Some might be tempted to write something like this for traveling twin, but you can't do that. You can only do that for the first part of the journey. But at a turnaround, the traveling twin would take a different path through space-time, so it would look like this. This scenario is identical to the situation where you have triplets A, B and C, and you connect the space-time diagram to the triplet C, that is moving indefinitely to the right, and want to measure the elapsed time on the clock of the triplet A and B. And of course, since the triplet C is inertial the whole time, his measurements would be in accordance with the measurements of the observer A. Some people just set the initial position of the observer C here and make him move in the opposite direction, where he reads the clock of the observer B and carries it to the observer A. But you don't even need to introduce another observers. I told you that special relativity is about measurements of inertial observers, but you can also derive how to do measurements if you are accelerated. In such case, you would use Rindler coordinates. You would slice the trip into three parts. The inertial one, the acceleration part, where you use Rindler coordinates, and in these coordinates the observer A would make this weird move through space-time, and then inertial coordinates back. If you did the mathematics, then you would get the correct result for the traveling twin. So where is the problem then? Why there is still argument whether we need general relativity to solve the paradox? And the reason is simple, because special relativity doesn't tell you which frame is inertial and which one is not. All these scenarios that I showed you were already predefined in a way that we already know which frames are inertial and which one are accelerated. You might say that I can pull out this accelerometer, and by this accelerometer I can see whether I am inertial or not. But if you look at the postulates of special relativity, there is nothing that tells you what this behavior means. In special relativity, every frame is inertial by default, unless it's said otherwise. Remember, it's a theory about inertial frames after all. And therefore, the moment we sketch a spacetime diagram like this, we define at least one inertial frame, and therefore all measurements are well defined. Acceleration is absolute, and therefore there is no paradox whatsoever in special relativity. If you want to have a paradox, you must deny yourself this information about which frame is inertial. In real world, you would have only two bodies in relative motion, and at one point, one of the observers experiences a force. If you want to use just special relativity, you have no tools to interpret this force, because special relativity is a theory only about measurements of distances and time. Special relativity doesn't tell you why you should be younger just because you experience a force. And that is a paradox, because both twins can claim to be stationary and they measure the other one as moving when they use their own clocks and rulers. To solve the paradox, you have to add equivalence principle into the mix. And then the observer who is feeling the force can interpret it as being in a uniform gravitational field. And since the observer A is higher up in this field, his clock ticks faster, according to gravitational time dilation. But there is still not full consensus whether a gravitational time dilation can be derived purely from equivalence principle, or you need a full theory of general relativity. I will put the link to the article in the video description. But if you can rigorously derive this gravitational time dilation just from equivalence principle, then you don't need general relativity to solve the paradox. Because equivalence principle alone doesn't mean general relativity. In the other case, you do. While it's true that in special relativity, the twin who is feeling the force is always younger, in curved space-time this is no longer true. You have to look at the field globally. For example, observer on Earth would also feel acceleration during the whole trip. Why should he be older? It's because the gravitational field the Earth produces isn't uniform. It has a negligible impact at large distances, whereas the observer accelerated in a rocket detects a uniform gravitational field spanning the entire universe. Another thing is that, to be younger, you must accelerate and see the other observer being ahead of you. For example, if you were hovering above the Earth and one observer would be in orbit around the planet, it would be him who would be younger at the reunion, since he was lower in the gravitational field. However, an observer that was shot upwards and is freely falling back would be older, since he was ahead of accelerating observer. So, feeling the force is not ultimate determining factor of saying who is older and who is younger when we consider the curved space-time, but in special relativity it is. The reason is that in general relativity it is no longer true that non-zero 4 acceleration also means non-zero 3 acceleration and vice versa. There is a lot to talk about in terms of general relativity and twin paradox, but I don't want this video to be too long. So, to summarize all of what I said, all explanations using triplets or Rindler coordinates are identical, because they have already predefined inertial frames, and the rest is just mathematics. In the case of using Rindler frames though, the mathematics is a bit more involved because you have to use calculus. And you are basically using infinityplets, since you make an infinite amount of small Lorentz transformations. To have a paradox, you have to deny yourself this information about which twin is inertial and which one is not. And only work with how could the observers themselves solve it using their rulers, clocks and other devices like accelerometer. And I know that it might be trivial to determine which frame is inertial and which one is not, right? But is it really? In ideal flat space-time, maybe it is, because really, if you're feeling the force, then you know you are not inertial. But in real world, it's sometimes more tricky than that. If you took, for example, clocks on two planes and make them travel around the Earth and back to the original position, to which plane you would attribute this straight word line? You might be tempted to give it to the observer that remained at the same location, but the Earth is also rotating. And if you account for this, the most inertial observer is actually the plane that is moving in opposite direction. And it would record the least amount of elapsed time, which was also measured. But that's for another video. If you are interested in twin paradox more, then check out my video about it. Thanks for watching and subscribe if you like the content.